Hi there, everybody. Welcome back to another Chem Complete lecture. And in today's lecture, we are going to continue learning about alkenes, and we are going to take a look at the halohydrin formation of alkenes, which is where we're going to add a halogen, and we are also going to do this in the presence of water to get a corresponding alkyl halide and alcohol functional group. So we are going to take a look at this reaction and all of its details coming up on the channel right now. Thank you so much for choosing Chem Complete for all your learning needs today. Now, before I start with this reaction, it is very important that you have gone through and you have learned the dihalide addition, which is where we simply add Cl2 or Br2 to an alkene without the presence of water. If you haven't looked at that, I would strongly encourage you to do so. I will leave a link down in the box below to that video, or if you are on the alkenes playlist, you should be able to get a hold of it. It is almost identical to this exact reaction, and so it will save you a lot of time and understanding if you view that first. All right, so that being said, let's go ahead and get started with this one. So the halohydrin formation is going to be the addition of Cl2 or Br2 in the presence of water. So essentially it's going to be a dihalide addition, but this time we are going to have water present instead of just the halogen material itself. So we'll start with an alkene, and the alkene will first be exposed to the, sorry, I don't like that bond. The alkene will first be exposed to the halogen, and then it will also subsequently have water exposure. So similar to the dihalide reaction, I'm going to go ahead and stick with bromine for this particular example. And what we end up with is we are going to get a halogen addition. So we will create an alkyl halide here. But then the other portionality, instead of a second halide coming on, we are going to end up with an alcohol group. And that alcohol group will be the result of water coming in and adding to the compound. So again, as I mentioned in the opening here, this is very similar to the dihalide mechanism. However, when water attacks in the second step, that is going to be the big difference between the remaining halide ion attacking versus the water, which will give the alcohol group. Now, similar to the dihalide addition, because water must attack opposite the halide ion intermediate, we are going to observe 100% anti-stereochemistry in this reaction, meaning that the bromine or chlorine will add on the opposite face or the opposite side of the molecule that the alcohol will. So let's take a look at this mechanism. Again, if you're familiar with the dihalide mechanism, you should be pretty well set with this, but we're going to walk through this one in detail here. So we will have our alkene, and for this example, I'm going to use a 5-membered ring, and we will put a methyl group on one of these two alkene positions, and that's because I want to differentiate the substitution pattern when we look at this mechanism. We then have the Br2. So again, this could be Cl2. It would work in a similar fashion if you were doing Cl2. And the first step is exactly identical to the dihalide addition, where you will get one of the halides to leave, and then you will get a reach out from the pi bond to the other one, and it will reach back in order to form its 3-membered intermediate. So what I'm going to create now is the Bromonium ion that we see resulting in a dihalide addition, and the methyl group, I'm going to draw that back here. So we've had our Bromonium form on the front portion or the top portion of this ring structure. Okay, and don't forget that this intermediate is charged. We do want to have a positive on that bromine. So if you were following along in the dihalide addition, we noted that when you have a more substituted position, that will be the position of attack because we're going to get a partial positive buildup. And so the same thing applies here. When we get ready to release this bromonium ion, we are going to get a partial positive buildup on this carbon in the ring, this top carbon right here, because it's more substituted. Now here's the big difference. Instead of the Br minus coming in, the water will behave as a nucleophile instead when we're in this environment, and the water will come in and attack the carbon that is letting go of the bromonium ion. So what we end up with is another intermediate. Now, some students have a tendency to cut this portion out and they just go directly to the alcohol. And that is problematic because we did not send OH minus in here. We sent in water. And when water comes in, you need to make sure that water is what's going to attach here. So here's the methyl group that's been inverted to the front. But in the back, instead of OH, I have water that has added. Now it's going to become OH in this next step. Okay, but the water's here, and again, important to have the positive on that oxygen. Water was neutral, it gave away electrons, so now it is positive. So another water, and some students will ask, well, why doesn't Br minus come in? You could show that. However, HBr, the resulting conjugate, is a strong acid and will just become H3O plus in solution anyway. So this kind of directly goes right to the acid that should be in solution. Another H2O will come and grab this acidic proton here, and then these electrons can go back to the oxygen so that it is now neutral instead of positive in that resulting water. And what we get with the removal of that hydrogen is our final product, and we now have an alcohol and an alkyl halide, in this case a bromine, that have added. So the alcohol should still be in back here. The methyl group would be in the front. Okay, and again, that is due to the size of this bromonium ion. We had to have the water come in the back because of steric constraints. And then over here, I would have the Br, and I would have that, what was originally an implied H that I'm just showing here now. Okay, so anti, we've got one here and one here, front and back. We get 100% anti-addition in this mechanism. Now, one other point that I want to make here is that because the OH will always add to the more substituted position, the OH group will always observe Markovnikov for the regiochemistry. So that is to say the alcohol group will always add to the more substituted position when we are dealing with this reaction. Okay, now this is a bit of a shorter video. I'm pretty much done here because, again, if you have studied the dihalide reaction, this is very similar other than that final step, which involves the water coming in and then the alcohol being delivered in this final step here. Okay, so anti-stereochemistry 100% of the time, and the alcohol will always land in the more substituted position, making it a Markovnikov result for the regiochemistry. So that is it. Please, if you liked this video, drop a like because it will help boost our content in the algorithm. Subscribing will keep you up to date and is a great way to support the channel. And if you'd really like to support us, you can head on over to chemcomplete.com. There are lots of guides, walkthroughs, different items for purchase over there for only $5, $10, $15, something very, very affordable, and it greatly supports the channel and the work that I'm doing. Other than that, if you comment or have any questions, I'll try to get back to you. And ChemComplete also has lots of free resources as well. So head on over there, visit. Even if you don't plan to buy anything, you can poke around and see what free resources are available out there for you. So other than that, thank you so much for learning with me, and I will see everybody in the next lecture.